Hi everyone, welcome to the video lesson for Thursday and Friday, October 22nd and 23rd. We started things right off with a warm-up that referenced our last day in class. So I pointed out that laser pointers can be pretty dangerous. They come in a lot of different colors, and I'm highlighting the green and red type. So according to the electromagnetic spectrum, which type of laser pointer would be more dangerous, a green one or a red one? Or in other words, what I'm asking is, which type of light has more energy? And then I asked, which type of light has a longer wavelength, infrared or ultraviolet? Now, this is not the sort of thing that I expect anyone to have memorized. That's why I said to go to your notes, so you could look at this chart, and you could compare those different answers. So our first question was about the laser pointer. So notice everything on this side is pretty low energy wavelengths. Everything over here is pretty high energy wavelengths. So then here's my visible light spectrum. We have my red light right here, and my green light's kind of in the middle. So red light is on the lower energy side, green light would be on the higher energy side, so the answer was green. My green light would have more energy in it than a red light laser pointer. Then the next question was about the wavelength of ultraviolet rays versus infrared. So here's my infrared, kind of spaced out waves, and then my ultraviolet. Notice as I go towards gamma, as I go towards ultraviolet, I get shorter and shorter wavelengths. So my infrared is going to have a much longer wavelength than my ultraviolet. After our warm-up, we went back to our notes and we continued taking notes on the atomic spectra. Then I introduced and started talking about our writing task about the atomic spectra. And I also started talking about our flame test lab. Both all task assignments are due on Tuesday. So before I got to our new notes, I went back to slide 5 and just wanted to refresh our memory about the continuous spectrum versus a line spectrum. So a continuous spectrum has all of the lights in the rainbow. It has everything, all the reds, all the yellows, all the greens, all the blues. All the light is there. A line spectrum has gaps. It has those black gaps. It only has a few of the light colors represented. So here I've got my iron. Make that bigger for us. Here we have a lot of blue lights and purple, a lot of greens. We're kind of missing a big chunk of the blue right there. We've got a lot of reds, but we're also missing a lot of reds. So that's the difference between a line spectrum and a continuous spectrum. So every element has its own unique line spectrum that it gives off. It's all produced by our electrons, and since every element has a slightly different electron arrangement, they all have slightly different line spectra. So we can call these atomic emission spectra or line spectra. Spectra is the plural, spectrum is the singular. And it's a way that we actually use in laboratories to figure out what elements are in unknown compounds. This is used a lot in forensics. If they have a residue of an unknown substance, they will use a spectrometer to find out what are the different components. It's one of the ways we use. Now that also gives us a beautiful periodic table. So this periodic table shows us the emission spectra of each and every element. Now it's missing a few of the synthetic ones, and that's just because we haven't had a chance to find their emission spectra yet. We haven't had a big enough sample. But each and every element has its own unique spectra. Now, when we look at it with our bare eyes, we see just one color. Those colors combine to make one color. So something might look rather orange to our eyes, but it might actually have a good number of blue lines there. Or something might be rather blue or green, but it might actually have a lot of yellow and reds. So the emission spectra shows us exactly what element we're looking at, even though they can glow at very similar colors. So since I'm not able to bring all of my demo equipment home with me, we had to watch a video that shows different gaseous elements and what they look like when they're glowing. So let me show it to you now. So to start the video, our friendly scientist man has a white light. Now remember, white light is made up with all of the wavelengths of the spectrum. Now he's going to put a prism in front of it, and notice that prism separates the white light into all of the wavelengths of all of the visible colors. We have blues that merge into other blues, that merge into greens, into yellows, and into reds. So all of our light wavelengths are there. It is a continuous spectrum. Next, we move on to a tube of mercury gas. So once he runs electricity through this tube of gas, it starts to glow with a very white bluish color. But once we put the prism in front of it, it's going to separate that blue-white light into its atomic emission spectrum. So we can see that bluish-white light is made up of 3 different wavelengths. We have a wavelength of blue, a wavelength of green, and a wavelength of yellow. There are other elements that have a bluish glow when you light them up, but mercury is the only one with these spectral lines. Now, we have nitrogen gas, which gives us a very pretty kind of rose gold color. When we put the prism in front of our nitrogen gas, we see its atomic emission spectrum. Now we see a few lines of blue, a few of green, some orange, and some red. It has a little bit of each color, but again, it's not a continuous spectrum. I have individual wavelengths of each of these colors, and this pattern is unique to nitrogen. Neon is the next element on our list here. It's very well known for neon signs in shop windows. When we put a prism in front of our neon, we see a lot of yellows and oranges, just a tad of red. Not too surprising here, but still, the spectrum lines we're getting from neon are unique to neon. And lastly, we have hydrogen gas. When hydrogen gas is energized, we get this nice, pretty purple color. When we put a prism in front of it, now it breaks apart into its atomic spectra. We have 2 very distinct blue lines and a very distinct red line. There is also a yellow line, but this is a prism, not quite a spectroscope, so it is not perfectly accurate when trying to see and measure the different wavelengths of light that are coming from our atoms. So after the video, we return to our slides to take some more notes on just how those emission lines are made. So it all comes down to our electrons and what's happening to them. So we already learned on Monday and Tuesday that our electrons like to orbit the nucleus in energy levels. They want to be as close to the nucleus as possible, the lowest energy level possible. So the lowest energy level they can get, as close as they can get to the nucleus, that's called the ground state. Now, they would love to be on the first energy level, but remember, I can only fit 2 electrons on the first energy level. So the ground state isn't always the first energy level. For some electrons, it's the second, the third, the fourth. It's however close they were able to get to the nucleus when they're put onto a uncharged, unexcited atom. So it's wherever they start is the ground state. Now, I want to move it. If we're going to start at the ground state, clearly we're going to be changing where we are. So once I give it some energy, so I can heat up my atoms, I can run electricity through my atoms, I can heat them up with some more light. As soon as I give them some energy, those electrons can absorb the energy. Absorbing that energy makes my electron very energetic. It makes it move more. It jumps up to what's called the excited state. So it starts at the ground state, where it's calm and has low energy. When it absorbs energy, it can't stay at the ground state, and it jumps up to an excited state. So here it is. It started at the first energy level, my electron. Now it's on the third energy level, so absorbed energy and it jumped up. Now the problem is, it doesn't want to be there. It doesn't want to be at the excited state. It wants to be at the ground state. It wants to be where it's stable, where it's close to the nucleus. So the excited state is unstable. My electron does not want to be there. So it has to undo what happened to get it up there. It absorbed energy and went up to the excited state. So now it has to do the opposite, which is release energy so it can fall back down to the ground state. And that energy that gets shut out is light. It's energy in the form of light. Now, what we look at is the visible spectrum, but sometimes it shoots off infrared, ultraviolet. It depends on how much energy is being shut off from that atom. So every step up or down has its own specific amount of energy. So it costs a certain amount of energy to go from 1 to 2. It costs a different amount of energy to go from 4 and 5. These are all different distances. As I go further out, those energy levels actually get further and further apart. So my space between 5 and 6 is a lot further spaced out than my distance between 1 and 2. The longer those jumps, the more energy it takes to make that jump up, and the more energy it gives off when it falls back down. Now, every atom has its own unique arrangement. What we learned about on Monday and Tuesday was just the very beginning of how complex it can get. We just learned about how there's different energy levels, and there's so many electrons on each level. There's even further. There's different orbitals. There's different spins. When you go to a concert, you aren't just told first row, third row, second row. You're told a seat. So it gets a lot more complicated with our electrons as well. So every atom is able to have its own emission spectrum, its own series of lights. So I was lucky enough to be able to get back to Northwest High School on Wednesday, properly socially distanced. I was the only one there, and I was able to record myself walking around and doing another example to illustrate what's going on with the ground versus the excited state. So let's take a look.
So my electrons have energy. They're constantly moving. Now, they're typically just moving around in their energy level. They're orbiting the nucleus, getting as close as they can, getting the best seats in the house, best concert seats that they can, and they're moving, always moving. They always have energy. But sometimes you can give them more energy. So if you stick those atoms into some fire or run some electricity through it, those electrons start to absorb that energy. They start to move faster and faster, and they start to get more and more excited. They get so excited, they just can't stand still. It's like a kid, like a little kid with a lot of candy. They have just so much energy, and they just start to jump, and they can't contain it. They can't stay on the ground floor anymore. They're too excited. They're too energetic. They can't be on the ground, so they have to get away. They have to go somewhere. They're too excited. They're moving too much, so they're gonna bump into the other electrons. So they jump up. They jump up to the excited state. This is not a very stable place. Do I look stable to you? I don't want to be up here. This is too high. I want to be down on the ground. I want to be down on the ground where it's safe, where I'm stable. Up here, I could fall. I could get hurt. I don't want to be here. My electrons don't want to be here. My electrons don't want to be excited. They want to be down on the ground where it's safe, where it's close to the nucleus. That's where they want to be. I don't want to be up here. Neither do the electrons. We want to be safe on the ground, but we're too excited. We're too excited. We have too much energy. We're not allowed on the ground. If we have all this energy, we're just too energetic. So if I want to get back down, I have to get rid of this energy. My electrons have to give off that energy. They have to give it off as light. They have to give that energy back. It goes out as light, and then they're allowed to go back on the ground. But to get there, they have to fall. So now I'm back down in the ground state. I'm much more calm. I'm much more stable. This is where the electrons want to be. So now, until I give them more energy and start the process again, then they're going to have to jump up again. And if they don't want to be up, then they can fall back down. So once they lose their energy, they're back at the ground state, where it's stable, where they want to be.
Now, I hope you noticed that during this video, I got more and more energetic as an electron, as myself, was gaining more energy. I was trying to talk as fast as I could when I was up on the stool in the excited state. But as soon as I got down again, back to the ground state, I talked much slower, much more calm. This is a lot of fun to act out. So our new assignment today was the flame test lab. So in the flame test lab, what we typically do is we put different metal ions into a flame and we observe what flame colors they make, because different metallic ions will glow different colors thanks to their unique atomic spectra. Now, since we can't actually send these salts to you at your house and have you light things on fire without us being there with you, we've given you a video to watch instead. And as you watch the video, we want you to be as descriptive as possible in the flame colors. Now, saying that it made a red flame or an orange flame is a very bad observation. Some of these flame colors will be very similar to each other. Some of their colors will be very similar. So rather than just saying it made a red flame, say it made a orange red flame, or a light red flame, a pinkish red flame, a blue flame, blue-green, yellow-blue, green-blue. Try to be as descriptive as you can when saying what color flames these made, so you can better distinguish them. Because as you scroll down, our later questions will actually give you some unknown flames. So based on those notes that you took about the different ions, what could these ions be? What could be making these flames? It's okay if you're not entirely right. I'm going to look at what notes you took, see if it compares to what you've reported. And then I want you to think, what are some reasons you could have gotten the wrong ion? Why is this not a perfect way to run a lab like this? What are some ways that we can maybe do this better? And then the rest of the questions talk about what we just learned in our notes and spectroscopes. So that's like in the video when we were looking at the emission spectra, looking at those different lines that were produced. Now, to help you out, because I know that not everyone can open up YouTube links, depending on the browser you're working with, I've added a page here about Flame Test Lab resources. So if you expand all of these, you'll get the video embedded of the Flame Test Lab from the lab. I have my Flame Test GIF. This one's not the official answers for what colors they make, but it's a good second reference. And there's also an added video about spectroscopes, how we use spectroscopes and how they function, which might also help you out with some of those questions. And I made a small change. The writing task was underneath first class of the week. I've moved it to the second class of the week, part of our module, because the second class of this week is when you got the information to answer it. So this is another CAMI assignment. I want you to explain in your own words how electrons give off light to make a line spectrum. You need to make sure you include all of those terms in your explanation. Now, just a small tip as a teacher, if you were to bold or make those vocabulary words stand out in some way, makes it a little bit easier for a teacher to grade. Make sure we don't miss that you did in fact include those words. And on the bottom half, you're going to draw a picture and label it of an atom showing how it gives off that light. Now, we are not an art class. If your atom looks like this, I think that looks like a beautiful circle. What's really important to me is that you label it. You tell me what that is. What is that circle supposed to be? So don't worry too much about your artistic ability. I am not grading you on that. And also, you can use the circle tool if you want help making a nicer circle. What's important here is that you're able to label everything that's going on, and you're able to interpret it in some way. So we ended the class with some independent time so you could work on those assignments. A few of you were able to finish and hand them in during class. And everything is due on Tuesday. So I hope everyone is able to have a lovely weekend and make good choices, everyone, and stay safe.